Let's take a look at a third example here. And this one has to do with polyprotic acid, and that's the third one on your note. It says, what's the pH of a solution that has an initial concentration of carbonic acid, H2CO3, of 0.033 molar? First thing to keep in mind, H2CO3 is a diprotic acid. We have discussed this idea earlier, where some acids can donate more than one proton, and H2CO3 is one of them. It has two ionization steps. I'm writing down the two ionization steps right here. This one is the first one. It has that Ka value. The second one, and it has this Ka value. And again, you can check your Ka table to get these values. Just the same way as we talked about when we first start calculating this pH of acids, we say first, we got to write out all the reactions that produce H+. Now again, as I said before, we can ignore water, right? So water is always in the back of our mind, but we just don't really put it in because we know it doesn't really contribute a significant amount of H+. But now we actually have two different acids, if you will, in the solution. So we're going to have to rank them, and we rank them that this is rank number 1 because it has a higher Ka, and that's number 2. So we're going to start with that first reaction and just solve that first. We have our reaction, we have our ice table. We start with 0.033, no products initially. At equilibrium, we have the same setup that we've seen a few times now. It's X in this case because this is a weak acid, right? Our Ka is less than 1. Okay, setting up the Ka expression equals to X squared over 0.033 minus X equals to that Ka1 value. We can use our small k assumption, right? Saying that 0.033 minus X is about equal to 0.033, and then just solve at that point. When we solve, we get X equals 1.2 times 10 to the minus 4 molar, and that X represents the H plus in this case. If you go ahead and check this number, you'll find that it's within our 5% error, so we can use it to calculate pH. But should we ignore second dissociation step? Should we use it? Well, let's just use it now and see what happens. This is our second ionization step. The initial, I want to highlight here, is a little different. The initial is bicarbonate ion, HCO3 minus, H plus, and CO32 minus, or carbonate, right? Well, we had earlier produced H plus and bicarbonate. So numbers here come from that first solution, which is 1.2 times 10 to the minus 4. That's why I filled those out as those numbers. The carbonate is still 0. Reaction is still going to the right side because we don't have a product, so it's still minus X plus X plus X, still a weak acid. So at equilibrium, I have these numbers, and let me set that up equals to Ka2. So here's Ka2, H plus times carbonate over bicarbonate. We have two expressions in the equation where X is being compared to a number. So we can assume small k for both of them. If we do that, then basically that number will cancel out. So our X is just equal to Ka2, which is 4.7 times 10 to the minus 11. That's our carbonate ion. We're not being asked for carbonate ion, but in case you are, that will be your answer. Again, let's see, does it matter that we find this additional H plus that's being provided by that second dissociation? So our total H plus then would be 1.2 times 10 to the minus 4. That's from the first dissociation. And then 4.7 times 10 to the minus 11. That's the second one. So again, this is from first ionization. This is from the second ionization step of carbonic acid. You can tell that that second number is not going to change the value of the first number, right? Because it's so much smaller. So therefore, our final answer is just going to be 1.2 times 10 to the minus 4. So what is the lesson here? We can ignore that second dissociation step. Let me wrap up our discussion on the calculation of pH of acid by summarizing some of the important information that we learned from solving these problems. The first one here is that unless your acid is very dilute, I mean something like 10 to the minus 7 molar, you can ignore water autoionization. In fact, except in the first problem where we specifically looked at it, all the other problems we've been ignoring autoionization of water. When you have a mixture of acids, let's say you have two weak acids or you have a strong and a weak acid, the strongest acid, which means the largest Ka acid, right, will determine the pH. So you can add some of the weaker ones, but it's not going to change. The number is just so different that these other numbers for the weaker acids are going to be so much smaller compared to the strongest acid you have in your collection. So as it said here, dissociation of weaker acid may be ignored. And if you have polyprotic acid, unless the successive Ka value is less than or equal to 20, Typically, you can ignore the later dissociation. You can just use that first dissociation step to determine the total H plus, and that was just shown in that last problem. By the way, most of the time, the difference between successive Ka values, so you have Ka1 versus Ka2, a lot of times the Ka2 is going to be about 100,000 times smaller compared to Ka1. So you never have to worry about the fact that the second Ka might become important in your calculation of pH. Now, you need to keep in mind though, sometimes you are asked to calculate ions that are produced by the second dissociation step that are not H plus. Like in the problem that we just did, the second step produces H plus and carbonate. So if your concern is to calculate carbonate concentration, then you're going to have to calculate that second step, right? Because that's the only way you can figure out how much carbonate is present. But if your goal is pH, then you can ignore that second step.